reason is just that because the things that we're counting in the corollary were mapped into things we're counting into the theorem. And that's exactly, the latter corollary is exactly the kind of estimate that's needed to complete the square-free sieve on the discriminants of degree 5 on polynomials. But of course, there's nothing special about the degree 5. We could have made those matrices for any n, and so that completes the square-free sieve for polynomial discriminants. And then, in the case of, so that's the statement of the theorem again. You get about 36% of polynomials have square-free discriminant. And as I said, Lenz's conjecture is strictly weaker because you have to sieve less. And so that also implies Lenz's conjecture that the density of f, that's the z bracket x mod f of x, is the ring of integers in q bracket x mod f of x, is 6 over pi squared. Okay, I'll stop there. Thanks so much. Thank you. Yeah, so far it's always been that one additional. Just because of the nature of the problem, we isolate a p such that p squared is dividing it. Usually that p ends up being the additional invariant. Either that happens, or you just get a codimension 2 condition where Ekadel applies. But this is the first case, this polynomial discriminant case is the first one where we didn't get something explicitly codimension 2, but we could still use orbit counting to get the saving. But one or the other happens. Yeah, we've done many polynomials now using this, but it's not a systematic method yet, in the sense that I don't know if you ask the question on which polynomials does this method apply, I don't know how to answer that question. But on the other hand, many polynomials of interest for which we needed square-free values. So another place where this arose, suppose you have some family of curves, and you want to know what is the density of semi-stable curves inside that, or those that have discriminants that are square-free. That's a question that often arises, and we needed that for like Selmer group sieves, for example, in work with Weiho. We needed to know that in a certain family of curves, we had the correct density of square-free discriminant curves, so that we could sieve to semi-stable curves, for example. And somehow, adaptations of this method have always worked. And we've always been able to do it. There's always some kind of transformation that you can do or lift it somewhere so that you split apart those p's and then you're able to do the square-free sieve. But that's kind of an algebraic geometry question. What is the nature of the polynomial so that the places where you become a multiple of p squared for mod p squared reasons, is there some kind of algebraic geometric way of splitting those p's by a suitable change of variables so that you can apply either Ekadal or some kind of other counting method. But splitting apart those p's, it seems like in all the cases that we've ever wanted so far, we've been able to do it. The question is, can it always be done, or what are the classes of polynomials for which this method works on? Yeah, and that I don't know. Yeah, but it has worked on many other examples. Oh yeah. Yeah, that density can also be worked out by similar methods because it's only one Euler factor that's changing, only one place that's changing, and the sieve only requires the large primes. So any such question can also be answered by this, although I don't know the constant offhand. Yeah. Once you can do square free, you can also do cube free. I don't know the constant offhand. Yeah, but any strictly weaker sieve can also be done. Or that involves the same sieve for sufficiently large primes. Out. Right. Right, right. Right, right. Right, 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 right. Right, right. And I don't know. Yeah. Uh, yeah, as I said, any polynomial that we really needed to know the density of square free values, we worked hard enough, long enough. There was some transformation that we always found. That maybe all the polynomials that we were always interested in had this kind of structure that we were using secretly. But I don't know what that. I don't know. I feel like there should be some algebra geometric way of saying what the structure of the polynomial is that allows this kind of transformation. And I don't. But I don't know. I don't know how to say it. So, yeah. Yeah. Like what is exactly the property that we're using? Yeah. That's a great question. I don't know the answer to that. It's a great thing to think about.